things we're going to be having a look at in linear transformations with matrices. Today we will probably do maybe 2 of these things here. So we're going to use matrices to represent linear transformations, which I'm sure you're going to be able to work out pretty quickly with just me showing you a few things here, like what does a matrix do to space? What does it do to the XY space? We're going to look at matrices to represent specific transformations like reflections, rotations and enlargements, all those kinds of things that you come across with at GCSE. Notice how I haven't written translations here. You can't use a matrix to represent a translation. And then we're going to look at how you can do multiple transformations. So instead of just transforming space once, you can transform it and do lots of things. You can do a reflection and an enlargement. You can do many things. And then last of all, we're going to use inverse matrices, which you pretty much know what they're going to do already. An inverse matrix is going to undo whatever transformation you had done. So maybe you get given the result of something and they say the transformation was a rotation, put it back to normal. You use an inverse matrix to put it back to normal, okay? Does anybody remember what we said the determinant represented in matrix transformations, in 2-dimensional matrix transformations from the videos? Pardon?
If the determinant was 0 or 1.
That's in our equations topic that we did before. This is going way back to the 3 blue, 1 brown videos. Do you remember what the determinant represented in a transformation of space? It was the scale factor. The scale factor of what though, Sam? What? The scale factor of what? The lengths of the sides? The area? Or? Good. In 2 dimensions, it represented the scale factor of the area. In 3 dimensions, the determinant represented the scale factor of the volume. And we're going to see that pop up during this topic, okay? And in 1 dimension, it would represent the scale factor of just the length. So that's kind of why it makes sense. 1 dimension is length, 2 dimensions area, 3 dimensions volume. Okay, so linear transformations. This is just a little bit of background to what linear transformation actually means here. And I've got a particular matrix which is going to do a transformation, and we are going to apply it to any pair of coordinates. In fact, the reason it's any pair of coordinates is because I'm going to call it x and y to refer to the whole of the 2-dimensional plane. When I would multiply these things together, what would it produce? Or what does it produce? Multiplying these 2 matrices.
2 by 2 matrices.
Well, yeah, what do I get? What's the answer?
AX plus BY.
AX plus BY and CX plus DY that we have here. So this is actually what's happening to the coordinates, okay? The x coordinate is getting multiplied by A, and you're also adding on to that the y coordinate multiplied by B. This is just the representation of a linear transformation. So I've said here that the chapter is concerned with how we use matrices to represent some transformation of a point, and we write that coordinate as a vector. I think I've taught most of you guys vectors in the normal maths and how if you want to change it from a coordinate to a vector, we just obviously put it in that vertical orientation. Transforming a point xy simply involves multiplying it by some matrix. From above, we can see that multiplying by a matrix A represents the mapping T, and then we put a colon here. We are mapping the coordinates xy to give you these new coordinates that we have here, or this new vector that we have. And we're going to start seeing how they behave. We will see how we can use certain matrices to represent certain well-known transformations, e.g. taking xy to 3x, 3y. And that's going to represent an enlargement of scale factor 3 centered about the origin. And you can see that that's going to do that because the x-coordinate has been tripled and the y-coordinate has been tripled. And if you imagine a 2-dimensional plane and everything's coordinates are being tripled, it's getting 3 times bigger. Whatever that image is, it's going to get 3 times bigger. And we'll try and figure out what matrix will allow us to do that thing that we've got. This is some kind of background stuff here. We're talking about this as a linear transformation. I've written that AX plus BY is known as a linear combination of x and y, which is an algebraic form we saw in pure year 1 with straight line equations. Each row of the matrix we're multiplying by provides an instruction of how to generate each dimension of the new coordinate system in terms of the old dimensions. So that all sounds a bit complicated, but it's just saying that the new system of coordinates is being generated from the old system of coordinates here. There's nothing, it's a linear combination of the previous things that existed. And again, there's some kind of formal stuff that goes alongside this. We've said that if you have a function and you do that particular function to a, it is a linear function if you're just multiplying it by k for a particular constant, or if you can split it up into two separate functions. This is all probably quite abstract, but will make a bit more sense when we see it in context of some of those things that we've got there. So this is really what it means to be linear. It would satisfy these properties of being able to take out a scale from it and being able to split it into two separate additive parts. But don't concern yourself with that too much. That is not kind of like a fundamental thing of what we're looking at here. This is where it will start to make a little bit more sense, okay? So, I've said, number one, we can represent a translation, so taking a coordinate x, y, and just adding 4 to the x coordinate. We can represent that using a matrix multiplication. Can we do that, true or false? False, yeah. Do you remember what I said earlier? I said you cannot use matrices to represent a translation. If you think about that, we just said with the previous bit where you have a, b, c, d and x, y, that gave us ax plus by and cx plus dy. There's no way of getting an x plus 4 at the top, is there? It's always going to be in terms of the previous thing. That's what we said by a linear, what it means to be linear. We've then got here that matrices can represent transformations which increase or decrease the number of dimensions. E.g., it could transform a 3D point to get a 2D point. Do we think that's something that's true or false?
True.
True, yeah. What makes you say it's true? It is true.
Because I remember seeing the video where the thing that equals to a single length.
Yeah, exactly. We've seen things in the video before that has collapsed space down into a lower dimension, whether it was going from 3-dimensional space to 2-dimensional space or from 1 to 2. And the way this might look is you might do something like, I don't know, 1, 0, 2, 4, 0, 0 multiplied by x, y, z. And you can start to see what's going to happen there. What will happen? The z is going to get cancelled out. So this is going to represent something that's in 3-dimensional space. It's going to collapse down into something that is 2-dimensional space because of these zeros that we've got here. So a transformation can actually collapse space down in that kind of way as well, right? What else was I going to say about that? I mean, I guess we could just work out what this would be. So you've got x plus 2y, 4y, and that's it.
So could you increase the number of dimensions?
You could increase the number of dimensions. I suppose you'd have to have numbers here. Would you be able to do that? And it would have to be like x, y, 0. Could you increase the number of dimensions? I don't think you can increase the number of dimensions. I would need to look into that. But it's worth something. I think they talked about that in that 3 blue 1 brown video. I think they said
You could do it with the inverse though.
you could. I think you could do it with an inverse. That's something for me to think about. I'll see if I can have a think of that over the rest of the lesson. Right. The origin is unaffected by any linear transformation. What do we think? True or false? Thinking of what this definition is that we've got here. Imagine it didn't say x, y. Imagine it said origin. So if x was 0 and y was 0, what would you have on the right-hand side? 0, 0, 0. So if we were doing an ABCD transformation to the coordinate 0, 0, we get 0, 0. So it's never affected. So the origin is unaffected by any linear transformation is true. Now, if you see on the very first page that we've written, we had said that matrices can be used to represent reflections. The origin is not going to be affected for the reflections we look at. We're going to be looking at reflections through the origin. Rotations about the origin. We can't do rotations with matrices unless the origin is the point that remains fixed, okay? And enlargements with a center of the origin. So the key thing for these things is that the origin cannot move, it cannot be affected because it would need to have this kind of thing, which you can't do with a matrix. So we're now going to do a little bit of some practical stuff that might go alongside this, and then a very, very short go on just a couple of questions from the exercise. So we're going to try and find out some matrices that represent these linear transformations. So this first transformation T is taking an xy coordinate and transforming it to 2y plus x and 3x. So it's taking a coordinate and it's producing something else. Now I guess the way that we could think about this is we're going to try and find out what is this matrix that when you apply it to xy, you get 2y plus x and 3x. Now I'm going to rewrite this. I'm going to write this as x plus 2y and 3x plus 0y, which should then make the next step very easy. What's the matrix? 1, 2, 3, 0, because you obviously, when you multiply it, you'll have the 1x plus 2y, 3x plus 0y. So that's the matrix for part A. Our matrix is just going to be 1, 2, 3, 0. And for B, well, we're trying to find out the matrix that when you apply it to xy, you get 0x minus 2y, 3x plus y. So we get a 0, minus 2, 3, 1. And you can just double check that by multiplying the matrix. You get 0x minus 2y, great, and you get 3x plus y, which is just what we wanted right there. Okay. Oh, so I should say my matrix is 0, minus 2, 3, 1. Now, this is where it actually starts to have some meaning. So far, I'm just telling you random things. This is now going to actually apply. We're going to see what this matrix transformation does to a particular square. So it says a square has coordinates 1, 1, 3, 1, 3, 3, and 1, 3. Find the vertices of the image of S under the transformation given by the matrix M, blah, blah, blah. Sketch S and the image of S on a coordinate grid. Now, the original thing, does anybody know what's the name of the original thing before the transformation? The result is the image. Do you remember what the original thing is? You might have seen it before. Not sure? The original thing is called the object. So it goes from an object to an image. So if they ever ask you to find the object, they're asking you to do an inverse and to go back to whatever the original thing was. Now I'm going to draw on my coordinates for this square. One of them is at 1, 1. You can draw these on as well. If you've got different colours, that might be good. The other one is 3, 1. 1, 2. I've got one at 3, 3. And I've got one at this one, 1, 3. So there's my square. And we're going to try and find out what happens to them all. Now you'll notice the matrix that does the transforming is always written first. It's written first for a reason, just because of our definition of how we do matrix multiplication. You can do a 2 by 2 by a 2 by 1, but you can't do a 2 by 1 by a 2 by 2. If you remember about the dimensions of matrix multiplication, obviously it has to come first. So what we're going to do is we're going to do minus 1, 2, 2, 1, and we're going to transform each coordinate like this. Don't write this down yet, okay? Because I'm going to show you something different in a second. You could do each coordinate separately, okay? If you wanted to, you can do each coordinate separately. And this is the way that the book says it, and I just think it's silly. So if you're going to do it separately, I'll just show you one of them. You'd have minus 1 times 1, which is minus 1, plus 2, which is 1. And then you've got 2 times 1, plus 1 times 1, which is 3. So the 1, 1 coordinate, which was blue, is being mapped to 1, 3, which I'm going to mark here with a cross. Now, there is a better way of doing this. Can anybody suggest what would be a quicker way of doing this? Pardon? No, you could do it with the centre of the square, but we don't know that it's necessarily going to give us another square. It's nothing, I'm not asking for anything that's actually that different, so you're probably not even thinking of the right kinds of things. You don't need to do one coordinate at a time. You can do all four coordinates at the same time. So you can do it like this. As long as you can recognize that these are your separate coordinates here, you can just do it at the same time, because it's going to produce 1, 2, 3, 4 coordinates like that, okay? If you want to, you can put it into your calculator, or you can do it manually and see what happens here. So what should we do? Calculator? Just for the fun of it? Let's quickly have a go at doing this on the calculator. Transforming all these points. So let's go on my matrix. So I've got a 2 by 2, and then I've got a 2 by 4. So that's -1, 2, 2, 1, 3, 1, 1. Anyone done that already? Obviously, you can do this manually as well, but so you've got 1, -1, 3, 5, 3, 7, 9, 5. Yeah. So we can see that that was the blue coordinate. Whatever, you can see where they were. That one goes to that one, etc., etc. So the purple one has gone to -1, 7, which is here. The red one has gone from 3, 3 to 3, 9. My board is so bad, I can't see it very clearly. And my green one has gone from 1, 3 to 5, 5. So we can see now what's happened. It has indeed produced a square. It might not look very accurate because I can't really see very clearly on my board here whether those are like that. So it looks like it's produced a square. We would probably call this one S, and we would call this one, silly, the image we would call S dash, is probably the way that we normally see that, okay? So can you try and can you imagine what some of the transformations might have been here? There looks like there's definitely been some kind of rotation, definitely some kind of enlargement. There's probably a reflection as well, because if you look at the orientation, the pink and the green appear to have like switched as well. I know it's a long way back to remember. Yeah, it's like a combination of all three. It's probably a long way back to remember this, but in the video, do you remember there were some things where it looked like it was like flipping over and twisting around? It like did a full like, yeah, it like flattened and like twisted around and stretched. This is, I think, what's happening in this particular one that we've got here. So we've sketched those two things here. Now, I'm going to go further ahead than what the book suggests. The area of this one that we've got here, what's the area of this little square?
4.
Is 4. The area is 4. And the area of this one that we've got here, Well, we've got a little right angle triangle that's going on here. Can we find out what the length of one of these, this side is of the square from Pythagoras? What's the root 20? Good. So one of the sides is root 20. The other side is root 20. So the area is 20. Okay, predictions. What's the determinant going to be? 5. Let's see if the determinant of this is 5. So we're going to do the determinant of this. Is it 5? So you've got minus 1, minus 4, which is minus 5. So it's the magnitude of the determinant that will scale the area. The minus is to do with the fact that it's done that kind of schwum, like that kind of like inside out bit that you've seen in the video before. Because it does, if you do a negative scale factor from GCSE, it kind of goes backwards through the origin and comes out the other side. So that's a little bit of stuff that's going beyond this particular part of it.
Only the magnitude is left.
So the magnitude of the determinant is the scale factor. Cool. So I think I might ask you just do a couple of questions from exercise 7A here, and then we're going to push on because I think it's quite easy.